All right, welcome everyone. My name is Michael Shukis, and today I'll be helping you understand Huygen's principle. Now, Huygen's principle is really awesome. It can help us to understand why light, sound, and water have wave-like properties, and also can help us understand certain phenomena such as diffraction, reflection, and refraction. So Huygen's principle states that every point on a wavefront is a source of wavelets that spread out in the forward direction at the same speed as the wave itself. The new wavefront is a line tangent to all of the wavelets. Now this might seem complicated at first, but hopefully through today's discussion, I'll be able to help you understand what exactly this means. So let's start out with what a wavefront and what a wavelet is. So we've all been there. We've gone to a lake and thrown a big old rock in the middle of it. Let's just say with this diagram right here, this center point represents the rock. And we know that when that rock hits the water, waves will start to propagate out in every direction away from it. And these waves are circular. This is what a wavelet is. A wavelet is pretty much a wave that leaves a single point and will propagate outwards. And a wavefront is basically the front of that wave. So let's look at this from the side. Let's look at this at the perspective of this angle right here, but looking as if we're looking at the side of the lake and can see the water move up and down. So originally, at this point right here, the water is smooth, but as soon as that wave comes along, the water level will rise, and it'll fall. It'll rise again, and it'll fall. The high point is called the peak, and the low point, the trough. And that can be represented, the peak can be represented by this blue area right here, and the trough is somewhere in between the two blue areas. Now, this is for water, but the same can be used to model sound and light as well. And in the future, I'll be using red waves to represent the trough, or the peaks of the sound waves and light waves. So let's look at how these wave fronts are propagated. So in this case over here, these are the wave fronts, and we'll say the source is over here, and it is going from left to right. Now normally, of course, these wave fronts wouldn't be perfectly linear, perfectly parallel like this, but we'll just use this to simplify things. Now, according to Huygen's principle, every point on a wavefront is a source of wavelets. So let's look at that. For this wavefront right here, we can use thousands of different dots to represent different points where wavelets form. But for simplicity's sake, we'll draw just 3. So each of these wavelets then spread out in the forward direction at the same speed as the wave itself. So these wavelets will move forward all at the exact same speed. Sorry about my drawing, it's not ideal. Now what's cool is the next part of Huygen's principle. This new wavefront, the new wavefront is a line tangent to all the wavelets. And a quick reminder, tangent means a straight line or plane that touches a curve or curved surface at a point. So we'll take the furthest point, which is right here, and we'll draw a line tangent that connects all of them. And this is the new wavefront. The same could be said over here. And that wavefront, remember, is the peak of the wave, and in between would be the trough. So this is how wavefronts propagate, but instead, there's tons and tons of little points, and in the end, it'll create this fine line that represents the wavefront. Now, what happens if that wavefront hits a barrier that has a little slit in it? Well, this is the really cool part of an experiment done a long time ago that helped scientists understand that light actually behaves like a wave. So if that slit is really, really small, and I'm talking small on the level where it matches the wavelength of the light or sound or whatever is passing through it, it'll begin to act like a wave. So initially, these look like they're traveling linearly, and looks like they're parallel to each other. Now, a quick recap. Wavelength is the distance from peak to pink, right there. So if this wavelength matches this slit, then it'll appear like a wave. And let's look at that. We'll have very few points because it's such a small slit, and they'll produce these wavelets. But because it's so small, it'll all kind of come together into a single wavelet. And there we go. It'll look just like a wavelet. And because these areas don't have points, that'll make it look like a straight line. It'll now appear like a curved line, like an actual wavelet, just like the rock being thrown in the water. And thus, we can see the wave-like nature of anything that has those wave-like properties. Now, for sound, as we'll be looking in the next slide, sound can tend to have rather large wavelengths. And in this case, wavelengths are defined as areas of high pressure to another area of high pressure. These areas of high pressure are the peaks, and the areas of low pressure are the troughs. These wavelengths are really, really large. And so larger objects, such as the size of a door, can make it act just like a wave. And when it does this is called diffraction. This is when light will bend, kind of, or sound in this case. So let's look at this example over here. There's a man outside the house, and there's a man inside the house. Now, we all know that if this man was to shout and this door is open, this man would be able to hear it. Now, why is that? Well, diffraction, or Huygen's principle. Light, or sound in this case, sorry, would act like points right here. It will form in wavelets, and it will travel through the room like this. And as it reaches this barrier right here, again, remember the wavelength is similar to the slit that it is interacting with. So it'll propagate again like this in wavelets until it reaches the ear of this person right here. And so just like that, one can yell from one side of the house, and someone completely on the other with lots of barriers can still hear the person that's yelling. But if this man was to suddenly shine, let's say, a flashlight, this man would not be able to see it. Why is that? Well, again, it's diffraction, and it's the size of the opening that matters. Light tends to have an incredibly small wavelength. It can only interact with slits that have a very, very small width. In this case, the door is very, very large, very wide, and thus it acts almost like those parallel lines that I showed earlier. But if you were to decrease the width of this door, suddenly that light would act like a wavelet and tend to bend. So let's look at that through this example over here. In this case, not drawn to scale, of course. If it was drawn to scale, it'd probably look more like this, but with many different lines in between. That light would be able to have many different points in between this doorway. Each one would, of course, exhibit would be able to exhibit those wave-like natures right there in wavelets, and it would all combine to form a simple wavefront. And this wavefront would continue to go on in the direction that it's traveling. But let's look at this example over here, where the width of that slit is really, really small. In this case, let's say that only a single point can be formed, and because of that, there will be only a single wavelet pattern. And thus, we can see that it's bending in all directions. And so that light would diffract, and it would be able to be seen in all directions, well, most directions. And so this essentially is Huygen's principle. Stated again, every point on a wavefront is a source of wavelets that spread out in the forward direction at the same speed as the wave itself. And the new wavefront is a line tangent to all the wavelets. This principle helps us to understand why certain things such as light, sound, and water have wave-like principles, and how these waves tend to propagate. Now, Huygen's principle can also help us to understand other phenomena such as reflection and refraction. But I feel that's a bit deep for this course, and so if you have any interest, I'd direct you to the OpenStax physics textbook where you can learn more.